Thank you very much for the introduction, and even more so for the invitation and the very warm welcome. So my application is now finished from the University of Warsaw. I started my postdoc there in October, but what I'm going to talk about is contained in my PhD thesis that I did at the University of Warsaw. And so it's going to be joint work with my PhD supervisor, Paweł Goldstein, and from the University of Warsaw, and Piotr Hajłasz from the University of Pittsburgh. So they are responsible for my interest in approximate differentiability. They are also responsible for the black ink stains on my hands, because one of my ink pens spilled this morning, and they are the ones who made me switch to ink pens instead of regular pens. While we were working on that paper that I will present, they really nudged me to use fountain pens, and I said, yeah, but I do use fountain pens from time to time, but for special occasions, like if I write letters to my friends. And Piotr looked at me and said, for me, mathematics is special. I thought it's special for you too. And so the next day I switched. So before I go into this project of ours, I wanted to repeat some of the background that Nasi already presented, but I will repeat it quickly and from the point of view of a person who doesn't have a lot of background in physics. That's me. So in 1980s, John Ball introduced this framework of nonlinear elasticity that, to me, when I read his papers, look in the following way. We have this domain omega, and we come up, so our aim is to model deformations, like, for example, stretching a rubber band that Anna showed us. And we want to find this family of admissible mappings that model those deformations well. So, as Nastya said, an example of such a family that would model deformations well could be a family of homeomorphisms. But then we do want to minimize energy of this form in which derivative appears, so we need to have some sort of a derivative for this chosen family. And that's, in a sense, why this whole homeomorphisms with derivatives come into question. And of course, then the big question is what kind of a derivative we want to choose. But before we answer this one, one more thing. Once we minimize this energy among the admissible mappings, then again, as Nastya said, we might get out of this class of admissible mappings. And this is one problem that I guess also Anna will talk about. But in a sense, what's more interesting to the questions that I will pose in the framework of geometric function theory is once we see that minimizer, I don't really care about to which class it belongs, but I want to know if it still corresponds to a physical deformation. So, for example, if we assume that all of those admissible mappings they preserve orientation, then we would like the minimizer to preserve the orientation as well. So we would be very unhappy if we ended up in the limit with something that reverses orientation. So the question is, so the question is if the minimizer preserves orientation or not. And then the other one is, does it have this property that we would like deformations to have, that it maps sets of measure 0 onto sets of measure 0? This is the so-called Wood-and condition. And, well, it's a natural thing to want to have because, in the real world, matter is not really created out of nowhere. And this condition assumes exactly that set of measure 0 is not mapped onto a set of positive measure. So this nonlinear elasticity, it gives rise to questions that a lot of people find very interesting. For example, what are the properties of limits in different metrics of homeomorphisms? And I guess we'll learn a lot about weak limits from Nastya. I will focus more on uniform limits of homeomorphisms and on diffeomorphisms as well. Then the other question is, can we easily check if homeomorphism preserves or reverses orientation? Well, because if we want to check if the minimizer preserves orientation, then it would be nice to have an easy way to do that. And for diffeomorphisms, the recipe is really easy. We just look at the sign of the Jacobian. If it's positive, it preserves orientation. If it's negative, it reverses orientation. And we shall see that for homeomorphisms, the recipe is not that easy, and in fact, the recipe, I think, doesn't really exist. And then, as it often happens in mathematics, I think, well, the questions just appear out of the other questions. So we're just interested from the theoretical point of view. We just want to know, what can we say about Jacobians of homeomorphisms? And what can we say about derivatives of homeomorphisms? I will talk about approximate differentiability, approximate derivative, and the definition is the following one. So we look at a function defined on N, and we say it is approximately differentiable at point x if there exists a measurable set Ex such that x is a density point of the set, and I will break it for a moment here, just in case we speak different languages. I wanted to recall the definition of a density point. So it's the one here. X is a density point of the set Ex if this ratio goes to 0 while R goes to 0. So this means that at those really, really small scales, the set Ex fills up most of the neighborhood of the ball. And so we have to find this set Ex, which fills up most of the neighborhood of the point X. And the linear mapping L such that if we take the limit with y's that do belong to this special set Ex, and we look at this quantity, the limit will be 0. So this quantity is something that we all know from just checking the classical derivative. And now the difference is, of course, in this special set Ex. So we don't look at all sequences converging to X, we just look at some sequences converging to X. And from that, you can see that it's a weaker definition than the classical differentiability. I will use this d sub f to denote the approximate derivative.
So it depends on Ex?
No, it does not. So you can show it doesn't matter what kind of Ex you choose, as long as it is of full density at X, then the definition will always yield the same mapping. The same approximate derivative L, and it will be unique up to a set of measure 0.
We have a question.
Mm-hmm.
I don't understand why it is weaker, because if we take Ex to be the ball, that we recover the usual...
Exactly, but we can take Ex to be something less than a ball. So I'll show an example in a second. But first thing I wanted to say that I do not find this definition. This definition is a pointwise definition. That's also an important point. But it doesn't help us think in a geometric way about mappings which are almost everywhere approximately differentiable. This for this, I want to use the Whitman's theorem, which says that a mapping which is a function which is almost everywhere differentiable on set omega. It has this property that for any epsilon, you can find a C1 function f epsilon such that the set on which they do not coincide is greater or smaller than epsilon. This approximately, almost everywhere approximately differentiable functions, they coincide with C1 functions on those really, really large in measure sets. Those sets can be very, very twisted, and they might have horrible geometry. All we know is that they are large enough. Here's the example I promised. We see here a mapping from the ball onto this figure. And it's defined in the following way. This cusp thing, the purple one, it is mapped, all points from this purple cusp U are mapped onto x0. And the outside of the cusp is on the outside of the cusp, we just have identity. And this B minus the cusp, well, it's a set of which x is a density point. And so we can choose the density point we want here in set B minus U. And then the function is always identity. So it is then this quantity here will be 0 as we want in the limit. And so it is approximately differentiable at x naught, but it is not going to be classically differentiable at x naught. One of the reasons would be, for example, that if we look at this line here, okay, my line isn't really a line, but it's a line horizontal to the x-axis that passes through x naught. The classical partial derivative will not exist. The Weierstrass nowhere differentiable function is actually nowhere approximately differentiable. So the lack of differentiability of this function is, in a sense, really horrendous. And I wanted to mention that it's actually an old concept, the approximate derivative. It appeared in works of Hinton and Don Juan in 1916. And I think for quite a time, it used to be a contender for the best non-classical derivative. And then Sobolev took over. This is my hypothesis. And it's in line with what Nastya said, that Sobolev's spaces somehow fit a lot of frameworks really, really well. And in a sense, my talk will be about the fact that approximate derivative does not fit this framework all that well. And I just wanted to recall that if we have a function f, we say that it has that Sobolev, or often called weak, derivative g if for any phi which is a smooth compactly supported function, let's say with all happens phenomena, the integral of f phi is the same as the integral of phi. So we want this to hold for the weak, that is the Sobolev derivative, to exist. And this, in a sense, is a global property. So Nastya introduced Sobolev spaces that are a closure of C infinity with some norm. And the Sobolev derivative, I just wanted to write the formula, can be described with this formula, which is a global one. And as we saw before, the approximate derivative is a local one. And it has to be a local one, just like the classical differentiability is a local definition. And, well, I don't know, but I do believe that in some sense, the fact that this definition, the Sobolev definition, is a global one, it might do the magic that Nastya mentioned.
A question.
Mm-hmm.
This is the distributional derivative.
Yes.
And what if you multiply it with a small bump function to make it local? Does it then come nearer to the approximate differential?
Sorry, can you repeat?
You can localize distributional derivatives by multiplying with a bump function,
Yes.
which is just one in a small neighborhood. And if you do that to the distributional derivative, does it come nearer to the approximate differentiability?
Mm-hmm. So, okay,
I mean, just like wavefront sets are defined in that way.
You would replace the phi with the Hermits around.
I mean, I think in a sense this is a bit too involved to see the link. I mean, it is and it is not. Okay, so let me say one thing before I answer the question. Actually, Sobolev differentiability implies approximate differentiability. This is not immediate. It's not like you can just glance at the definition and see that, but it's true. And in a sense, I would say that you can see it via this approximation with bump functions. The fact that this definition implies this pointwise one that we had here. Did I more or less answer the question? Okay. So, well, I think that approximate derivative lost the battle to Sobolev, but I still think it's an important notion. And one of the reasons is that Sobolev functions are approximately differentiable almost everywhere, as they have just said. And also, if you've heard, there is also this other, in a sense, famous class of functions in calculus of variations, of functions of bounded variation. They are also almost ever approximately differentiable. Then the other reason, my favorite reason to be honest, is Federer's change of variable theorem. He proved it in 1944, and it says that this formula for change of variables, if we replace the classical Jacobian with the approximate Jacobian here, this holds for homeomorphisms, which are almost everywhere approximately differentiable, and which satisfy Wusian conditions, so which have the property that maps the set of measure zero onto a set of measure zero. And well, in a lot of books about Sobolev spaces, you can see a version of this theorem, but it's not so often traced back to Federer. And well, I like to use my talks as, in a sense, an advertisement for this theorem because it's extremely powerful. The proof is not really more difficult than the Lipschitz case that you can find in, I don't know, Evans and Gary book. And yes, it holds for this significant weakening of the statement for almost ever approximately differential homeomorphism. Then the other reason would be that approximately, almost ever approximately differentiable functions, they appear quite naturally as limits of C1 functions in this metric that I call the Wusian metric. It's a metric that measures the distance between f and e as the measure of the set on which they do not coincide. And it becomes a metric if we identify functions that coincide on sets of full metric. And so it actually follows from Whitney's theorem that this is the case, that if we take a limit of C1 functions in this metric, we'll get something which is almost ever approximately differentiable. And there's this classical theorem of Wusian that says that if we take the limit in this Wusian metric of continuous mappings, we'll end up with something measurable. So in a sense, well, this is more philosophical than mathematical, but in a sense, approximate differentiability is to C1 what measurability is to continue. I'll try. Approximate differentiability is to C1 what measurability is to continuity.
And it is multidimensional set. It's not only for dimension one.
It's in Rn. I mean, the n equal 1 is not really interesting, but n greater or equal than 2. And then I wanted to mention something that I don't know much about, but I know that approximate differentiability was also used to show some regularity results in Heisenberg groups. I know this paper of Paweł and Spade, and I'm not sure about the pronunciation of the last name. And I know there are a lot of people here that work in Lie groups, so I thought maybe that would be an interesting point to mention. Okay, so to finish this motivational and background section, I wanted to show you the big picture of what I find interesting in this research. So we have the analysis forest here and the topological one, and they do meet, for example, here. And I think of it as, in a sense, you know, like, for example, this recipe for orientation of differomorphisms. It's an obvious classical thing, and it's somewhere here. But what we have been, I mean, what the field is, in a sense, trying to do is building this bridge between analysis and topology over this lake of homeomorphisms. And I think of it in the following way. Well, homeomorphisms, they have a certain topological rigidity inside them. And the question is, can we see this rigidity in their analytic properties? Can we see it in their Jacobians? Can we see it in their derivatives? And well, that is supposed to resemble the view from the math department in the Vascula. In the wintertime, the lake is frozen now, and that's the bridge. And the math department is actually here, But then on the other side of the bridge, there's the physics department. So I'm not sure what their relationship with topology is, but I had to make it work for the picture, so that's how it looks like. In 2017, Paweł Goldstein and Piotr Hajłasz, they published a paper in which they showed that there exists an almost ever approximately differentiable homeomorphism of the unit cube that is again in n greater or equal than 2, such that it is identity on the boundary and the approximate derivative equals the reflection matrix almost everywhere. Moreover, it satisfies the Wilson condition n, so in a sense it's an admissible deformation, and it's also a uniform limit of C-infinity measure-preserving diffeomorphism. What do these first two properties tell us? The fact that a homeomorphism is identity on the boundary via a standard argument, it actually says that it is orientation preserving. So we have an orientation preserving homeomorphism, whose derivative is the reflection matrix almost everywhere, whose Jacobian is almost everywhere negative. So this shows that there is no link whatsoever between this analytical and topological properties of the homeomorphisms, which is bad news for approximate differentiability and bad news for that bridge from the previous slide. I wanted to mention here that that this question of the sign of Jacobian is also very interesting in the Sobolev case. So one could ask if we have a W1P homeomorphism between from omega into Rn, which preserves orientation, can the homeomorphism change sign? So can it be positive and negative on sets of measure 0? Can it be negative if the homeomorphism is orientation preserving? And the answer is actually very, very difficult. It depends on P and N, and it's not fully answered yet. And I would say that most of the answers are centered around Stanislav Hansen from the Charles University. In that paper,
This is one natural question, because everything should be almost everywhere.
Yes.
So isn't it possible to put anything on the boundary, or what is the constraint for that?
I mean, firstly, they wanted to have identity on the boundary. So, of course, you can put different things on the boundary. But they wanted to have identity on the boundary, and this is...
But if you have any, and you put identity, what it changes?
If I have any
homeomorphism, and you put then identity on the boundary.
But if I have a homeomorphism, a homeomorphism is always defined
because this should be almost...
No, but a
It's
homeomorphism...
almost the approximate
so
differentiable is
so
not
I see.
continuous.
So almost everywhere is differentiability, and
Yes.
homeomorphism is everywhere.
Yes.
Okay.
It's a real homeomorphism. It's defined everywhere, but the derivative is only defined up to a certain measure here. But this is in line with what I'm going to say now, because actually they also conjectured that, okay, but here we have the reflection matrix, could we put anything else here? And they conjectured that we can put a lot of other things there, and as they often are, they were right. So that's what we proved in a paper that has, I think, just been released in Advances in Mathematics. It's a theorem about the unit cube. So we have the unit cube in Rn again, and this measurable map T that goes from Q to GLN, so the space of n by n invertible matrices, and we assume this volume constraint here. So we assume that the integral over Q of the absolute value determinant of T equals 1, the volume of the unit cube. And prove that there exists an almost everywhere approximately differentiable homeomorphism phi, which is identity on the unit cube, so it's a homeomorphism of the unit cube, and whose approximate derivative equals T almost everywhere. This condition here, this is really necessary because of this Federer's change of variables theorem.
Should you make T somewhere not invertible?
So that's a very good question. I don't know. I would like to know, but I think it's a very difficult question. But it's not obvious that it couldn't be done, because there even are Sobolev homeomorphisms which have zero Jacobian almost everywhere. This is a paper by, again, Stanislav Hansel. So this restriction that T is in GLN, it does imply that determinant is non-zero everywhere or almost everywhere, and this is a real constraint. And this is something that we haven't even started to think about because the construction in this case is already really involved. But yes, it's an excellent question. What happens if the determinant is...
Could localize Federer's theorem, apply it to small balls, or
Let's come to that after I sketch the proof of this, because I mean, there's really a lot going on. And I mean, yeah, it's a very interesting problem. I would be surprised if there was an easy solution to that. Okay, so I basically covered the second dot here, but I wanted to say that in a sense that the moral of the theorem is that basically any sensible mapping can be the approximate derivative on almost every approximately differentiable homeomorphism. And by the sensible, I mean it has to satisfy the volume constraint, it has to, and this constraint on the determinant that we have just discussed. And one could ask, okay, we have that result with the reflection metric. Is it difficult to go from the reflection metric to any T? Because in a sense, it would sound as if the most difficult part was to go through this topological constraint, to do that to do that negative Jacobian while preserving the orientation. But it actually is way more difficult to prove this theorem than the previous one because of the difference of T on X. That makes it way more difficult to deal with than the case in which the derivative is linear and does not depend on X.
Excuse me, is in this theorem losing condition satisfied or not?
Yes. A lot of the questions precede what I'm going to say, so let me just show it on this slide. Yes. Phi does satisfy the Euclidean condition, and it's actually even better because it preserves sets of measure zero. So the image of a set of measure zero has measure zero, and the image of the set of measure zero has also measure zero. Moreover, phi inverse is also almost ever approximately differentiable, and the derivative is the one we would expect it to be. And last but definitely not least, phi is limited to infinity for phi k, which converges to phi in the uniform metric, which you can see here. And that last piece of information leaves us with the morale that uniform limits of diffeomorphisms can be whole. And I will come to that at the very end of my talk, but firstly, the promised sketch of the proof of theorem 2. So it actually starts with prescribing the derivative of a diffeomorphism. And we prove this theorem 3. We have a bounded domain. We have an orientation-preserving diffeomorphism between omega and f of omega. And we have T. Here T goes into GLN plus, so the determinant is positive. And we again have a volume constraint, which this time follows just from the classical change of variables, because we have diffeomorphisms here. And we prove that for any epsilon, there is a diffeomorphism phi, such that the boundary condition is satisfied, so phi equals f near the boundary of omega, and that derivative is prescribed. Here is the classical derivative of the set of big measure.
Maybe for the previous slide, but when that doesn't have to. So you mentioned that the main difficulty is the dependence T of X.
Mm-hmm.
So kind of, if you have a constant matrix, negative Jacobian, that is easy to get from the...
Yes, if you have a constant matrix, so the derivative is linear, then it's fairly easy to get it from this theorem.
Yeah, just clarify.
So this says that we are able, if we have a positive determinant here in T, we are able to construct differomorphisms with prescribed derivative up to sets of small maps. And I will just show quickly how it's done. So
Is the converse true of this theorem? I mean, is a uniform limit of differomorphisms approximately differentiable everywhere?
Yes, it will always be approximately differentiable. That follows from this Wuzin metric thing from witness theorem, but it might not be a homeomorphism. I mean, sorry, in this metric, it will be a homeomorphism because this metric guarantees injectivity in the limit. But if the injectivity is slightly more delicate, but it will always be approximately differential. I don't have much time. Okay, so I'll skip that. It's a constructive proof. And a very quick sketch of the proof of theorem 2. So the first thing is a reduction to the case in which the determinant is positive. And this is done by the smart use of this theorem 1, where the derivative is a reflection matrix. And then one could think, okay, so we have this theorem 3 that prescribes the derivative of the homomorphism. So could we not just iterate it and get the result? And the answer is no, because this naive iteration scheme, it does not yield injectivity in the limit, so it will not converge in this uniform metric. And here's the picture. So imagine we have phi k that has the correct derivative on this black set. And then this volume constraint here, it is satisfied for this set q minus ck, so this English set. However, well, there is no way we can control the diameter of this set. So if we want to use theorem 3 to prescribe the derivative in this pinkish set, to increase the set on which the derivative is prescribed, then this will mean moving points around the entire cube. So this will not guarantee uniform convergence of those phi k's. So we had to come up with a quite involved iteration scheme to make it possible for phi k's to be convergent in the uniform metric. And in a sense, the highlight of this iteration is that we construct a sequence of differomorphisms together with partitions, so that the derivative is correct on a large part of the cube, the diameter of each partition cell is small, and on those partition cells, this volume constraint holds. And so the question, of course, is how we construct the partitions. And now I will skip this. And that's, in a sense, the idea behind these constructions of those partitions. So we have a function f here that satisfies this volume constraint here. It is, this is not a homeomorphism anymore, I will just point it out. It's a function, it's a function defined on the cube. And there's a compact subset K of Q, on which f equals 1 almost everywhere. And we look at Q as consisting of those two cells, P1 and P2. The set K, in the end, is going to be that set on which the derivative is already prescribed. That is the set that we want to treasure, and we don't want to spoil the derivative there. And we prove that there exists a differomorphism psi. That's not the final differomorphism, that's just something that will help us along the way. It's a differomorphism of the cube, such that its identity near the boundary of the cube and an identity near a large part of the set K, and such that the integral over pi for both i's of f equals the measure of psi of pi. That's the picture, that this differomorphism psi, it pushes the wall between P1 and P2 so that in the end the cell has correct measure, the measure that is required by this function f here. So in a sense, this is about doing the construction in a way that at each step we prescribe the derivative, but we also correct the way in which this phi k distributes the measure so that we have room for prescribing the derivative further on. And it is, this lemma is heavily inspired by a very old theorem from 1944 by Euclidean Ulam. I think it's 1944, sorry, I misremember. The so-called homeomorphic measure theorem. This doesn't follow from homeomorphic measures theorem, but it's heavily inspired. It's a theorem that characterizes all measures which are homeomorphic to the Lebesgue measure in this sense that for any Borel set E, there is a homeomorphism H such that for any Borel set E, we have that the measure mu of E coincides with this. So you can see more or less that there is a correlation here. And here, I wanted to say a sentence that I never thought I would, that topology helps, but it does. There is a very important corollary from the Brouwer's invariance of domain theorem that says that if we have two domains, omega and omega prime in Rn, and a homeomorphism acting between their closures, then f of the boundary of omega is the boundary of omega prime, and f of omega is omega prime. So in other words, homeomorphisms map boundaries to boundaries and interiors to interiors. And this underpins most of the constructions with it, and it is my belief that it actually underpins most of constructions of homeomorphisms everywhere, because this just makes it much, much more easy to correct them, to glue them, to imagine what the image is. And to finish, I wanted to say that, this theorem too about prescribing the approximate derivative of homeomorphism, Piotr said that it's a theorem that's really beautiful, but really useless. And I would like to convince you that it's not as useless as he says. First of all, it does leaves us with the morale that approximate differentiability might not be so useful in nonlinear elasticity. So Sobolev wins here in this case. Then it makes you appreciate the positive results more, and I guess we're going to hear about those from Nastya and Anna, in the sense that by these positive results, I mean results that show that in this jungle of really, really weird limits, you can see some structure, and you can find assumptions that actually allow us to model something using limits of Sobolev homeomorphisms, for example, or some other admissible classes of mappings. It could be useful in other constructions. I actually recently needed this to realize that the claim that I was working on is false. And it gives rise to further questions. And here I won't show the example that I had because I'm running out of time, but I would quote the example that we discussed during the talk, that it would be also really interesting to know what happens if the determinant of t is 0. Could we...
15 minutes. The questions are included in...
Oh, I thought I have to leave 10 minutes for questions.
As soon as possible.
If I ask you a question, what do you want to say it more and then...
Then I feel a bit sorry for the proof that I rushed through it so quickly, but okay. So one interesting open question is the one we discussed, and another one is the following one. So let's have T that has points determinant and satisfy the volume constraint. Does there exist a homeomorphism phi, again, of the unit cube, identity on the boundary, which is differentiable almost everywhere, but here classically differentiable and not approximately differentiable, such that the derivative equals t almost everywhere? There is no obvious reason why that shouldn't be true. There is no obvious way to see from the construction that we have if by assume T to be in GLN plus, we can get something which is differentiable almost everywhere. And I know I rushed through the proof, but I still hope that you got the sense that there's a lot going on in the proof. So it's not easy to see from the proof that we have. However, it is standard to see that it wouldn't be true if the determinant is negative on the set of positive measure, because that follows from degree theory that this couldn't happen, because if we have an orientation preserving homeomorphism, then the classical derivative has to have, the classical Jacobian has to have positive sign. So that's the open question that I wanted to finish with. So I guess I will thank you for your attention, and